Okay, so on this question number 2, I will first focus. I could read the entire question, but I'm not going to start by reading the entire question. I'll start off by doing number 2A1. Why? Because it can be done without me reading the entire question. I'll go back, of course, to read the entire question, noticing some important things which we must learn. The first part, number 2A1, says, show that the vertical component of the tension in the string is 2.4 newtons. So I'll come to the string. The string has a force of 4.8. How do we know? Because it is labeled, firstly. Secondly, it was said that the tension in the string is 4.8 newtons. So we are being asked to find the vertical component of the force in the string. So what do we do? Vertical component, of course, it will be like this, in this direction. So the first thing is that we have the tension in the string itself is 4.8 newtons. Now, to resolve it vertically, we have to consider that the angle that this tension which I'm indicating by this red, the angle that it makes with the horizontal is 30 degrees. So the rule of thumb that I use is this one. If you are to resolve any force or any vector in a direction where the angle is not given, for example, I want to resolve it in the vertical direction, but I don't know this angle here. Of course, I could find it, but I don't know this angle here. Since I don't know this angle here, I'm going to have to use the angle that is known, which is on the other side, 30. In that case, I use sine. But if I was resolving horizontally to find the horizontal component of this tension, whereby the angle 30 is known between the tension and the horizontal to be 30, I would use cos. So here, to resolve, I'm going to say that it is 4.8 sine 30. Sine 30 is half. So half of 4.8 is 2.4 newtons. So we have shown what the question wanted us to show. The next part says, by taking moments about the hinge, determine the weight of the beam. In this case, now I need to read the question now. A uniform rigid beam, when a beam is ever said to be uniform, the first thing that must come to your mind is that this means that its weight acts at the geometric center. Of course, here they already did it for you. For example, from this hinge to where the weight is indicated to be acting, there is 0.5 plus 0.1, which is actually 0.6 meters. And from here, where the weight is acting to the other end, there is 0.2 plus 0.4, which is again 0.6. So that's the geometric center where the weight is acting. But even if they had not given you those distances, if you knew, let's say, the total length of the rod, if you are told that it's a uniform beam, then you know very well that its weight will act at the center of gravity, which is at the geometric center. Anyway, let's continue. A compressed spring exerts a force of 8.2 newtons vertically upwards on the horizontal beam. So that spring there, as you can see, that spring there is applying a force vertically here at this point of 8.2 newtons. A block of weight 0.30 newtons rests on the beam. I believe we can see that one. And then the right hand end of the beam is connected to the ground by a string at an angle 30 degrees to the horizontal. The tension in the string is 4.8 newtons. The distances along the beam are shown in Fig 2.1. The beam is in equilibrium. By implying that the beam is in equilibrium, this statement alone that the beam is in equilibrium is an open-shuttered statement By saying the beam is in equilibrium, it means that, number one, the resultant force in any direction on the beam is zero, which means that the forces acting vertically upwards on the beam are equal to the forces acting vertically downwards on the beam. Number two, the forces acting horizontally to the right on the beam are equal to the forces acting horizontally to the left on the beam. We could go further with that. Then the other condition is that if it is in equilibrium, then anti-clockwise moments are equal to the sum of the clockwise moments about any axis or pivot that you might choose on the beam. The anti-clockwise moments will be equal to the clockwise moments. So that is the implication that the beam is in equilibrium. And then you're also told that assume that the hinge is frictionless, meaning that there's not going to be a friction force on the hinge there. So then the question comes and says, by taking moments about the hinge, determine the weight of the beam. So by telling you that about the hinge, the question is telling you that you are going to take the hinge as your pivot. And if you're going to take the hinge as the pivot, then we are going to ignore any force that acts at the hinge. Reason being, any force that is acting through the pivot, any force whose line of action that goes through the hinge or pivot or axis, that force perpendicular distance from the pivot is zero. So since moment is force times perpendicular distance from the pivot, if the perpendicular distance from the pivot is zero, then that force which acts through the hinge, through the pivot, through the axis, has no moment about that pivot. So we will ignore any force acting through the hinge in this particular case and focus on the remaining forces, which I'm going to highlight shortly. So the three forces which we're going to focus on is the force here due to the spring, the force due to the weight of the beam, the force due to this block, and then the force due to the tension. And we are going to apply the definition of moment. A moment of a force is the force multiplied by its perpendicular distance from the pivot. So before we do that one now, we need to establish which ones of these forces are causing clockwise or anti-clockwise moment. So if you look at these forces carefully, which you're going to do, you can see that this force due to the spring will go like this, and considering the pivot to be here, this will cause a rotation of the beam in this direction. So the force here causes an anti-clockwise moment. Then the next one which we deal with is the next force. The force here will cause a moment like this, will cause the beam to move like this. So this one causes a clockwise moment. Then the next one causes again a clockwise moment. And then the next one causes again a clockwise moment, as they are all going in the same direction, as you can see. So to cut the long story short, we are going to now apply and say, okay, this force which is causing the anti-clockwise moment, what is its value? Its value is 8.2. And what is its perpendicular distance from the pivot? 0.5. So its moment is 8.2 times 0.5. Then the next one is the weight W, which we don't know yet. But what is its perpendicular distance from the pivot? Its perpendicular distance from the pivot is 0.6. Remember, the beam is horizontal, and if the beam is horizontal and the weight acts vertically downwards, then it's obvious that the angle between the distance from the pivot to the where the force is acting, the weight is acting, is these make 90 degrees to each other. So if that is the case, then we are going to say weight W times 0.6. And then up next is the block. It has a weight of 0.3, and this perpendicular distance from the pivot, this one, is 0.5 plus 0.1 plus 0.2, which gives us 0.8. So ultimately, this gives us a total of 0.8 distance, perpendicular distance from the pivot, times the force of 0.3. Now finally we are left with one force, and that force is a force of 4.8. Now I'm teaching it this way, and I always teach it this way. We need to find this perpendicular distance from the pivot, but we have a problem. This force, its perpendicular distance from the pivot cannot be this one, for the simple reason that that distance and the direction of the force, they don't make an angle of 90 degrees with each other. The angle from here, as I showed you, is not 90 degrees. At best, it is 180 minus 30, which is 150 degrees. So that creates a problem now, because the definition of the moment of a force says force times perpendicular distance from the pivot. So what do? We need to find the perpendicular distance of the force to the pivot, or from the force to the pivot. So in other words, the distance should make 90 degrees with the direction of the force. Now, what do we call direction of the force? Obviously, in red, if you check, the force is acting here. But even though the force is acting here, this entire arrow is showing you the direction of the force. Yes, of course, it's a string. There's a tension in that string. But as far as the beam is concerned, the force on the beam is acting here. That's a fact. So ultimately, the string simply represents the direction of the force. So the line of action of the force. So I can draw the same line of action of the force going backwards, like that. And if I do it this way, going backwards like that, if I draw now a line from the pivot, we can have a situation now where the line of action of the force, the direction of the force, the direction where the force is going, and a distance from the pivot are making 90 degrees to each other. So remember, a force is a vector. So when we're talking about the perpendicular distance from the force to the pivot, we are considering the force itself, which is a vector. Number one, its magnitude and its direction. So if I'm saying a perpendicular distance from the force, we are actually talking about a distance which makes 90 degrees to the direction of the force. Because for the force, there are two things, magnitude and direction. The only thing that you can make 90 degrees to is not the magnitude of the force, but rather the direction of the force. So that's why I'm able to draw a line that continues backwards from the direction of the force, which still indicates the direction of the force. So I can put an arrow there to indicate that this is the direction of the force, which has not changed. And now we have a distance here, which I can label x, which indicates a distance which is at 90 degrees to the direction of the force, which is the same thing as saying at 90 degrees to the force. So that's a perpendicular distance. So we want to find that perpendicular distance. And as there's an angle of 30 here, there will be an angle of 30 here. And if that's the case, that there's an angle of 30 degrees there, and there's an angle of 30 degrees there, then it means that we have to consider and continue to the next stage. And what is the next stage? The next stage in this case will be to find this force here, this distance, or x. Now, since we already know this distance from here to here, it's 1.2 meters. To find that, and we have a right angle triangle here. So the distance x is opposite to the angle 30. So we want to find that opposite, and we have an hypotenuse of 1.2. So obviously we use sine theta. So we come here, we stop for a while, and we say, okay, sine theta, or since we know that theta is 30, sine 30 is opposite, which is x, over hypotenuse, which is 1.2. So the x which we are looking, which is the perpendicular distance, will be 1.2 times sine 30. So now we have found our perpendicular distance. So I'll come here and I will say times sine, times 1.2 sine that, making sure that my calculator is in degrees. When all is said and done, maybe we can even go simpler. We can simplify everything, and then, when we simplify everything, ultimately, we will have to take everything else to the other side. We will say W times 0.6 is equals to 8.2 times 0.5 minus 0.8 times 0.3 minus again 4.8 times 1.2 times sine that. And if you do this, what do you get? You will get and if you do this, you will get you ultimately get that W is equals to 1.6 newtons. So you come here, you write your answer, 1.6, since the newtons is already there. Now the next question says, calculate the horizontal component of the force exerted on the beam by the hinge. Calculate the horizontal component of the force exerted on the beam by the hinge. Now, we have to start again here. Now, the question that may trouble you is, how am I going to find a force being exerted on the hinge by the beam? So the beam, in a way, is acting on the hinge. Now, if the beam is going to be acting on the hinge, then the hinge is also going to be acting on the beam by Newton's third law with an equal and opposite force horizontally. Because they want a horizontal force acting on the hinge by the beam. So there must be a horizontal force acting on the beam by the hinge. So on that basis, since we're told that this is in equilibrium, then we have to consider that if it is in equilibrium, how many forces are acting on this beam horizontally besides this obvious force from the hinge, which is acting horizontally on the beam? What is the other forces acting on the beam horizontally? And we will notice that the force due to the weight here, due to the spring here, is acting vertically, so it has no horizontal component. Weight vertically has no horizontal component. The block here, its weight 0.3 vertically, no horizontal component. But the tension here has a horizontal component. And in trying to find the horizontal component, in this case, since 30 is between the tension in the string and the horizontal side, we use cos. So the component then will be 4.8 cos 30. So to round this up down now, we will say the force acting on the beam by the hinge. Since the beam is in equilibrium, the force acting on the hinge by the beam, obviously, let's call it maybe A, minus the force acting on the beam by the component of the tension, that is horizontal. Let's just say that force is what? 4.8 cos that. If we subtract these two, we should get 0. Why? Because the beam is in equilibrium. So the resultant force horizontal itself is also 0. So A, therefore, will be equal to 4.8 cos that, which will give us 4.2 newtons. So the next thing is, the spring obeys Hooke's law and has an elastic potential energy of 0.32. So that spring, which has a force of 8.2 in it, has an elastic potential energy, which it is storing, of 0.32. Calculate the compression of the spring. So we want to know how compressed the spring is. Now, we write the formula for elastic potential energy. Elastic potential energy is equal to half the force that is applied on a spring multiplied by the extension x or the compression x. Now, we are given the elastic potential energy. So this is a piece of cake, this question. With the elastic potential energy is 0.32. We are also given the force acting on the spring. We know it. It's it's actually 8.2. So the compression, it's then easy to find. So we multiply 0.32 multiplied by 2 divided by 8.2 to give us x. So our value of x after calculation will be 0.078 meters. And then we continue with the question. The string is cut so that the spring extends upwards. This causes the beam to rotate and launch the block into the air. The block reaches its maximum height and then falls back to the ground. Okay, so I'll continue with this question so that this video is not too long. I'll continue with this question.